Our first speaker will be Dr. Ian Bryden, who will be speaking on tidal power, and he's with the Robert Gordon University from the United Kingdom. Welcome, Ian.
Good afternoon. The title of the talk claims to be tidal power, but I'll make one slight modification to it. It certainly is tidal power, but almost everything I refer to over the next 30 minutes is actually on tidal current power, which is really a subset of the overall. And as you'll see, it is actually a very difficult form of renewable energy to harness, which raises questions about why are we actually looking at this in the United Kingdom. And then you have a look at government policy, which says that by 2010, the United Kingdom should be generating 10% of renewable energy from of its electrical generation from renewable sources. And by 2020, we should be doing 20%. Now, I'm based in Scotland, and the Scottish Government has decided to do things rather differently. And they've said that by 2020, 40% of our electricity will be generated from renewable sources. And as we're already reaching a planning blockage with onshore wind power, there's a substantial incentive to look at alternatives to the alternatives, including wave power and tidal current power. Now, tidal current power and tidal power in general is not a new concept. Here we've got a potted history of the development of tidal power. Top left-hand side, take us back to 450 AD, the Elling Tide Mill, which was built by the Romans in the south of England, still working incidentally. You can actually buy flour ground at the Elling Tide Mill. Move forward a bit, top right-hand corner into the 60s. You're looking at Lorence in northern France, substantial tidal barrage project, still operating. It's just gone through a major refit. But the two lower images are really what I will be referring to, tidal current technology. Bottom left-hand side, it's a device undergoing maintenance in the Bristol Channel. It's called Seaflow. More about that later. And I'll say an awful lot more about the one in the bottom right-hand side, which gives you a clue as to who actually designed it. Tidal currents. What kind of resource is it? Let's have a look at the world distribution. This is a map of the distribution of energy dissipation from tidal currents around the world. And rather uniquely for me, I can't actually find the United Kingdom in it. I think we're tucked away in the top right-hand corner. I got this map from NASA, and they have a slightly different world view than those of us who live in Aberdeen. The rule is, the redder and the blacker, the more energy there is already being dissipated, simply dissipated into immeasurable increases in heat and temperature around the world. So this is a widespread but not homogeneous energy source. How much energy are we talking about? Well, most people talk about, oh, right, here's a good incentive. These are tidal currents in Yell Sound in the north of Scotland. That's a stationary vessel, by the way. I'm very, very glad that the loudspeaker was off, because one of my technicians was in the back coming out with sort of language that really does not deserve to be repeated in polite company. I don't think you actually realise how much energy there is there. This is a substantial resource. Yell Sound is one of the best sites, but it's far from being the biggest or the most convenient. Energy. Most people talk about kinetic energy in moving water, and the right-hand image there is actually one of my favourite tidal current sites in Scotland. It's Ainhallow Sound, between the mainland of Orkney and the island of Rousey, just off Orkney. It's about 1 kilometre wide, about 40 metres deep, and I'll look at some of the statistics of that particular area. If we look purely at the kinetic flux, we have an equation. That's the only equation I have on this presentation. Equation for the kinetic flux in a channel with moving water. It's actually wrong. Not only am I giving you one equation, I'm giving you a wrong equation, because I'm afraid the energy available from tidal currents is not purely kinetic. And in fact, the wrongness of that equation has quite literally global significance into the environmental acceptability of tidal current energy. More about that later. Let's move on. The statistics of Ainhallow Sound. 1,000 metres wide, 40 metres deep. I'm sorry, I've expressed these power capacities in terms of Scotland's two largest cities, Edinburgh and Glasgow. Relatively small channel. If we look at the kinetic energy flux, and I'll stress the word kinetic in there, flowing through this channel as a function of flow speed. At about 2.5 meters per second, the kinetic energy in that channel is roughly equivalent to the mean electricity consumption of the city of Edinburgh, a city of about 500,000. Take that up to 3 meters per second, and you're getting to the mean electricity consumption of the city of Glasgow. If you actually do the sums, you'll find that we tend to use about half as much average electricity per person as the United States. So you could multiply these up or reduce the size of the city whatsoever. But that's misleading, because the tidal currents, although totally predictable, I can predict tidal current speeds 30,000 years into the future, 300,000, 3 million years into the future, I presume, and very profound implications to the applicability of storage for this particular resource. But although predictable, they're not constant. They're variable. We have the diurnal cycle, the semi-diurnal cycle, we have the spring-neap cycle, etc., etc. And if you plot the influence, particularly of the magnitude of the spring peaks and the neap peaks, you'll find you certainly don't get a particularly flat surface. If you want to assess the energy that's available in a good tidal source site, you really need to know detailed knowledge about the statistics. And this is a mistake that many potential developers have fallen into. There are some sites with very, very good spring statistics and lousy neap statistics. You need both to be fairly energetic. A rule of thumb, a good site will have the average spring peak about twice the average neap peak, but we don't worry too much. One of the advantages of living in the British Isles, a maritime country, is that the waters about the UK have been surveyed to death over the past 300 years. And the Department of Trade and Industry have already gone so far as producing a map of the energy flux density from tidal currents. In the left-hand side, we see the average spring tide flux statistics. In the right-hand side, the average neap statistics. I find this a very, very misleading map, because it suggests all the tidal current energy is round about the south of England, west coast of Wales, or the east of England, whereas a closer investigation will find almost all of it is round the Scottish coastline, almost invisible on that map. It's to do with the resolution and the density of the energy flux. It looks as if there's only a couple of sites in Scotland, but my goodness, they're big ones, as we'll discover later on. Okay, so if I want to assess the quality of a site, I need to look at the energy, obviously, but the time variation is going to be very significant. I need to look at how the current speeds vary in space as well. We'll find some apparently good sites have hotspots that move about through the tidal cycle. That's not good if you're wanting to put a tidal current device into the water. So you really need to be looking at areas of high energy and high spatial and temporal stability. Now, one such site is the Pentland Firth, which lies between Orkney and the north coast of Scotland. It's if you look at the left-hand side map, the right-hand side map shows you Yell Sound, which was the location of the short video. I actually worked out the peak kinetic energy flux through the Pentland Firth is of the order of about 80 gigawatts. So you're not talking small quantities of energy here. And don't worry about slowing the rotational speed of the Earth. I can actually prove mathematically that that won't happen. Now, if we want to be able to assess the quality of a site, we need to be able to have a look at the distribution. I hope this is going to work. This is a numerical model of the Pentland Firth. It shows you how the intensity of the flow varies throughout a single day, a single tidal cycle. The darker, the more energetic. Most of that area, there are drastic changes in positional distribution, but there is one area which lies between the two small islands in the middle, in which the flow is spatially stable and temporally predictable. And that's the most exciting area for tidal current power, certainly in British waters. But if we want to move on, we have to actually look at what happens when we take energy out of this area. The map on the right-hand side there is actually back to Yell Sound. It's a numerical model that's been set up to have a look at the implications of extracting energy from the tidal flow. This requires, regrettably, a solution of the full Navier-Stokes equation, which all of my students hate, and they've got actually another name for it, something else I can't actually repeat, but it's rather rude. And they've been working on that and also developing equivalent laboratory tests, building large flow models of the Pentland Firth. There's a lot of water sloshing around my laboratory at the moment. And what we find is that a site like Yell Sound, Pentland Firth, actually behaves quite well when you take energy out. And there's a few things happen that are really quite surprising. Now, I won't take you through these simple simulations in detail, but the lower one shows a channel in which you're taking 10% of the kinetic energy flux out. In the middle, the grey area, is where I'm going to be taking that energy out. Bizarrely enough, you actually find that the flow speed downstream from the turbines is actually faster than the flow speed upstream from the tidal turbines. I try and explain this to wind power engineers, and they actually try to have me committed, which I'm not really in favour of. But this is very, very significant, again, from the point of view of the global energy balance. And it really tells you that tidal current energy extraction is not really extracting kinetic energy. It's extracting something else. I talk about total energy of the tidal flows. It's why tidal current power is not the same as wind power. Wind power, you simply skim energy from the bottom of the atmosphere, and most of the atmosphere is not affected. Tidal current power, you're taking energy from the bulk flow itself. And as long as you remember that, you should be okay. Here we've got the consequences of some of the numerical modelling. We have the influence of energy extraction and current speed. This is actually for Yell Sound, demonstrating that if I take something like 20% of the kinetic energy flux, I'll stress that, the kinetic energy flux, you get about a 6% overall speed reduction. Now, 20 years of measuring flows at sea, I can't actually measure tidal currents to that level of accuracy, because the variation in the flow speed on a second-by-second level is considerably bigger than 6%. So, from the point of view of the mechanical engineer, which I am, 6% variation in flow speed is no variation in flow speed, because it's considerably less than the natural fluctuations. Okay, if we take this kind of understanding and take it into assessment of just how big the resource is, we can, well, you can come up with any number you want, basically. I got myself into terrible trouble at a presentation to the Scottish Executive a couple of years ago, where I said that any assessment of the tidal current or wave power resource in Britain conducted before October 2004 was a pile of rubbish. And the reason for that was that's actually when I published the methodology that you should be using. I really wish I hadn't said that to that particular audience. It took me off a few people's Christmas card lists. But never mind. The Carbon Trust in the UK actually published what I believe was the first reliable assessment of the tidal current resource. They came up with something like 22 terawatt hours per year, readily accessible tidal current energy in the United Kingdom, about 6% of the UK's electricity consumption. With science fiction technology that's not even on the drawing board yet, those figures could well prove to be pessimistic. Now, this is small compared to wind. The potential wind resource is far, far bigger than that. But the wind resource is diffuse in comparison. Some of the energy flux densities we are looking at are of the order of 150 kilowatts per square metre, the type of flux density that the wind engineers can't even dream about. So we are looking at potential of substantial production with relatively small developments. And in renewable energy, the smaller you can make your technology, the cheaper it will be. So there's an intriguing possibility there. Let's move on. I've not talked about the technology at all yet. There's a bit of a problem here. Unlike wind power, we've not got technological coalescence yet. We still don't know what the commercial technology would look like. I've given you 4 options here. Horizontal axis turbines, very like wind devices. Vertical axis turbines, type of thing the wind industry was playing with about 60, 70 years ago. Maybe they might come back. A couple of other options I've seen proposed, Venturi-based devices, relying on acceleration of flow through a Venturi tube. I've tried doing the sums on that one, and I can't actually get any energy out of a Venturi device. Linear lift devices in which you take a turbine and you stretch it out into a flat blade. I actually, if anybody twists my arm, I think we're probably looking at horizontal axis turbines for future development. The turbine is not the biggest problem. I'm not a turbine designer, but I've got a book on my shelf which I can take down, and I can produce a turbine design that's probably only 3% less efficient than the best open water turbine you can get. The big technical problem is making sure the blasted thing doesn't wash away in the flow. Are we going to use gravity bases? Are we going to drill into the seabed? Are we going to use pile jackets? Are we going to use floating system? The jury is still out on that, and it probably is a function of water depth as to which approach we're going to use. I'll take you through a quick historical overview here. As far as I'm concerned, this is when it started, 1990s, very early 1990s. A mid-water tethered turbine. It's interesting who paid for it. Scottish Nuclear, now part of British Energy. Interesting synergy between the nuclear industry and the renewable industry. Early 90s. The next serious device was this one, NMR, in 2000 in the Strait of Messina between Sicily and the Italian mainland. A vertical axis turbine tethered to the seabed. Slip forward another 10 years. We have Seaflow, produced by a company called Marine Current Turbines Limited. To all intents and purposes, as you can see in the image on the right, it's very much like an underwater wind turbine. I get very upset when I say that, because the mechanical engineering of it is actually quite different from a wind turbine. This thing has been generating more or less continuously since it went into the water. It's working with a capacity factor of between 65 and 75%, which for a mechanical renewable energy source is almost unbelievable, and without incident. So far, probably the most successful of the tidal current devices. We will get failures with this technology. This is a device that's been tried and, let's say, didn't meet its designer's requirement. This is a linear lift device. Takes power out, a bit like a whale's tail drives a whale. It oscillates vertically, pumping hydraulic fluid. It used simple gravity to hold it in place, instead of being drilled into the seabed like Seaflow. There's plenty of other devices, however. Move to Norway. This device is generating right now, Hammerfest Strom, at the entrance to a fjord. Superficially quite similar to Seaflow, but it relies on diver intervention, which actually scares the living daylights out of me, the idea of diving in the vicinity of one of these things. But it works. It's producing electricity into the Norwegian grid. Technology that hasn't made it yet, perhaps. On the left-hand side here, we have a Venturi device being tested in Grimsby Harbour, of all places. The right-hand side is a heavily ducted horizontal axis turbine, rated at 2 megawatts, which is due to go into the sea early in 2006. I'll say a bit more about where it's going into the sea in a minute. Here's another device, a tethered horizontal axis turbine. This should also be going into the sea about the middle of 2006. It's again intended as a deep water concept, unlike Seaflow, which is intended as a shallow water device. And many of the most energetic sites, such as the Pentland Firth, have water depths of the order of 100 to 150 metres water depth. This is my little baby, the snail, or as my students call it, Brian. The snail is actually a glorified anchor, which is intended to hold any generic turbine to the seabed. Remember what I said the big technical problem was? How to hold these things in the seabed cheaply and safely. This thing simply uses reversible foils, presses it down to the seabed. In 3 metres per second water current, those foils produce about 200 tonnes effective downforce. The thing in air weighs 23 tonnes. Huge advantages operationally. I can install this with a harbour tug at a day rate of £3,000 per day. To use the type of vessel that you need for Seaflow, you're talking about £80,000 per day. Economics is important. Where do we test these devices? Well, in the UK, we've established an organisation known as the European Marine Energy Centre. Typical UK, sort of, we just put European in front of it so we can get EU money. This is actually Orkney. Please don't quote me on that, by the way. This is the islands of Orkney to the north of Scotland, and this is the other side of the Pentland Firth, a phenomenal tidal current resource, phenomenal wave resource. We've now established 4 grid-connected points for wave power devices and 5 grid-connected points for tidal current devices. They are intended for type testing of technology at full scale. Already, as we're talking, there is one megawatt wave power device generating power into the grid in Orkney, and 2 tidal current devices will be going in, as I mentioned earlier, in 2006, again connecting into the grid. Challenges, we're not there yet. That's our biggest challenge. The distribution of population and energy consumption in the British Isles. And very, very few of those bright blobs sit on top of good sites for either wave or tidal current. So I've now said the grid word. Grid is important here. How are we going to manage this? Another one, of course, tidal currents, although they're predictable, they're still variable. However, the economics of tidal current generation, if you could even store an hour of generation from these devices, starts to change rapidly. We move from a soft renewable source to a hard renewable source, capable of displacing firm capacity. So the holy grail of storage comes back into the fore. Storage in a highly predictable resource, and a device that only has a dead period of about an hour, hour and a half every 24 hours. Starts to sound quite significant. Other issues. Installation, I've already mentioned. This is a difficult and dangerous environment to work in. You can only seriously install this technology during slack water, about 45 minutes in most locations. The snail, we can get that down in 30 minutes, and we can retrieve it in about 45 minutes. That's why it was designed. Intervention, maintenance, we've got these very short periods where we can actually retrieve the equipment, and there are still question marks about erosion and corrosion. Maintenance is still a major issue here. It has to be said there are some environmental issues. How will it interact with marine life? Within the Supergen consortium, of which I'm the leader, this is one of the main areas that we're currently looking at. Are we going to chop seals up? The answer is no, and I think I can prove it to you. Whether I can prove it to the environmental lobby, who seem to like seals, is another matter. Flow impedance modification, just the fact that we do slow the flow. What's the environmental implication of that? Well, I can now prove that we won't slow the Earth up, if that's what's worrying anybody. And of course, with any type of engineering work going into a delicate habitat, just what will the installation and maintenance work, what problems will they cause? Environmental concerns. Economic challenges, the next one. The economists within the Supergen programme tell us that the best are looking at about 8 pence per kilowatt hour, which is still about twice what it needs to be. That's even with the sale of the UK incentive known as the Renewable Obligation Certificates. If you want to know about them and you don't know about them, ask me later. It'll take me about 3 hours to explain it. And that's assuming I don't forget halfway through. So we're not quite at the point where the renewable obligation market in the UK can quite make these economic. But ultimately, the cost curve is heading down. And there are serious predictions that said we're probably only about 3 years away from direct competition with wind. I want to leave you with a thought. And I know there are social scientists in the audience, so please don't get offended. I'm a mechanical engineer. I don't understand these things. There's the UK population distribution. My enemy, effectively. What is giving the marine renewables and wind a bit of a problem in the UK? People are not living in the right place. It's very antisocial of them. Now, let's just add something to that. The distribution of coal fields in the UK. Almost everybody living in the United Kingdom is living more or less on top of a coal field, with the exception of London. Now, that's not accidental, because during the Industrial Revolution, the jobs moved to where the energy was, and then the people moved to where the energy was. So perhaps a vision, 200 years' time, Thurso, in the north coast of Scotland, is the capital of the European Union. this tumbleweed blowing through the streets of London, Edinburgh, Paris, Berlin, as we redistribute ourselves to where the new energy lies, as opposed to the old. Thank you.
Thank you very much. We have time for a few questions.
I got two questions, both brief. Is the tidal fence project in the Philippines still happening? And the second question is, has anybody thought about putting a wind turbine on top of a tidal generator for a co-located structure?
Okay, the first question, I've been trying to find the answer to that for about 12 months. And I've been in contact with Blue Energy, and they tell me it is happening, but I don't know what stage it's at. So I will wait and see. Tidal current turbines, however, with respect to wind, because of the concentration of that resource, you really want to get these turbines fairly close together, much closer together than you would want wind turbines to be. So whereas I think it could be done, I'm not sure what the economic advantage would be, because you want your wind turbines to be further apart than tidal turbines. So it may have some attractions, but probably not as much as you might immediately think.
Yes. Do you can you tell us a little bit about the typical daily and seasonal variation of tidal power?
Okay. It depends on your location, obviously. Places like the Pentland Firth, heavily dominated by the semi-diurnal tides, more or less twice a day. So you get 4 tide direction changes every day. You lose probably, you fall below the cut-in speed for a tidal turbine, maybe about 40 minutes at each slack water. You're also governed by the spring neap cycle, which means that over a 14-day period you get a variation between the spring tide and the neap tide. There are other cycles, but they're far less significant than the semi-diurnal, than the bi-monthly cycle. So they are variable, but we can predict them, you know, an indefinite period into the future.
Regarding the energy, you thought we are not extracting the kinetic energy from the water. No. So what we are extracting then?
Well, I talk about the total energy flux in a tidal current. And when you do the full modelling, I showed you earlier on the slide of the energy dissipation through tidal currents. You're actually extracting, bizarrely enough, a potential energy flux, because the kinetic energy flux downstream is higher than the kinetic energy flux upstream, which is totally bizarre. It just doesn't make sense until you start looking at it in fine detail. What you're really doing is just redistributing that energy extraction. I've tried to vary the models as much as I can, and the only effect that seems to be happening is that you're concentrating the energy dissipation where your tidal device is, and you actually lower the energy dissipation probably for a couple of kilometres around. So you're not increasing the total extraction of energy from the tidal currents around the world, which is why I say you won't slow the Earth down. In fact, one particular scenario I did actually found that by taking about 50 megawatts out in one location, I actually reduced the total energy extraction from the environment. So if anything, I was sorting a problem that we didn't even know existed.
Thank you very much. Next up, our next speaker is Dr. Arnold Stux from the Naval Research Labs, who will be speaking on nanomaterials for battery applications. Welcome.
Good afternoon. Thank you all for attending this afternoon session on energy and nanotechnology, specifically nanomaterials. For this presentation, I'd like to talk a bit about nanomaterials for battery applications, and it's an honor for me to be here today to participate in this discussion. So there's different energy storage methods, and we've already heard a lot about the need for grid energy storage. We'd want to mitigate the effects of blackouts, for example, and increase reliability. We've heard some things about peak shaving and load leveling applications. And so we really need to meet these demands for the fluctuations in power. And the angle, I guess, that I'm coming from here is our battery technologies and lowering the cost. And this involves innovation in national labs and research institutions and small businesses. And just on the right here, I just list a few different types of energy storage methods. I think you've all seen the list several times, but we've heard a lot about superconductivity, for example, and the focus will be, for my talk, on batteries. Now, when we talk about grid technology or alternate energy, we can think of off-grid power, and specifically here, I'd just like to just talk about some military uses of off-grid power. On the left is an example of use of fuel cells operating laptop computers and battery chargers. This was at the Civilian Military Operations Center. Actually, this was a huge operation that involved several countries, the private sector and the government. This was a simulation of a refugee crisis. For example, if there's civil unrest or any military confrontation. And this actually took place in Hawaii, on the big island of Hawaii, in a desert area. And so these are some examples of alternate energy being put to use. And then on the right, this is an example of a hybrid fuel cell system used with a solar cell. Actually, the fuel cells and the solar cells were used in parallel to recharge some nickel metal hydride batteries, and the nickel metal hydride were supposed to power the radio equipment used. So this was an undertaking that involved many different organizations. So now, when we talk about alternate power and energy, we can consider the range of different types of energy. Clearly, in the context of this two-day-long meeting about energy for the grid, we would be talking about power for the really far to the right end of the spectrum on the large scale. But I'd just like to throw out some just feasible battery technologies that correspond to different scales and different ranges based on just a few issues of cost and duty cycle, for example, and just what is needed, what the job is needed to be done. For example, we can consider personal power. Like this might be an example of just using a battery at the store, a primary battery, or in the case of soldiers here, using the BA 5590. These are the soldiers have to carry a lot of equipment, and one big issue with that is that the batteries take up a lot of weight, and so there's a lot of interest in reducing the weight for the batteries for that application. So on the small scale, if you talk about rechargeables, you could talk about lithium-ion technology, and lithium cobalt oxide is a standard material that's used. The downside to that is it's very expensive and for the high scale. So there's been work on partially substituting cobalt with nickel and manganese and the like. And there's a lot of research on nanomaterials for lithium-ion batteries, and I'll get into that more in detail. But then we can also consider use of power on the level of a home or generators. And for this, lead acid might be more feasible. And I just had a conversation a couple nights ago about use of batteries on planes, on unmanned air vehicles, and one problem is that there's oxygen there, and with lithium-ion batteries, there's a problem with the sealing and some kind of adverse reactions. So there are definite considerations. And then for cars, the use of hybrids, we could consider nickel metal hydride and lithium-ion batteries for use in that application as well. But then on the large scale, for alternate power and substations and the like, sodium sulfur is an example of something, and this has been used in Japan, and I think it's already been mentioned, use of flow batteries and lead acid. So I think this just gives an idea of the different range and different types of technology. So what this, all these pictures really amount to is you need the right battery for the right job. Now, I just wanted to talk about batteries and some background. Some of you might have a background in batteries already, but really they're just, you have the anode and cathode, and it's a charge storage device, so you have to separate these two electrodes electronically, but there needs to be an electrolyte which connects them ionically. So lithium ions, for example, and lithium-ion batteries can transfer back and forth between these electrodes. But there are other parts of the battery too, such as the packaging and the interconnects. If you have to scale up a battery and you need a certain voltage or a certain current, you'd be talking about connecting a number of individual cells in parallel or series. And I show here for the example of lithium cobalt oxide and lithium ion batteries that the energy stored is right here in the cobalt 4 plus, which when you discharge, then you would be reducing that part of the cobalt back to 3 plus. And then just some background on primaries and secondaries. You might hear secondary means rechargeable, and a primary you can really only discharge once. So now I talked about power and energy, and I'd just like to clarify these terms, because specific energy, when we talk about batteries, is usually referred to in units of watt-hours per kilogram. And whereas specific power, that's how much energy you can use in a small amount of time. For example, if you have a very small battery, like a sensor, something that needs to transmit, but then can take a lot of power, but then remain in a standby mode, this kind of duty cycle, which require a lot of power. And there's no Moore's law. Basically, how much material, how much capacity you have in a battery depends on how much material. So the more material, the more capacity. The specific capacity of a material used in a battery is an intrinsic property of the material. And typically, the faster you discharge a battery, the lower specific energy you have. And there are some systems that are robust to fast discharge and don't lose that much specific energy, but generally that's the case. Specific energy is highest when batteries are discharged at low rates, and generally primary batteries can be considered as having more energy than secondary ones, but the disadvantage is they can't be recharged. So I just show here, just in the blue, some nickel metal, the rechargeable technologies, and nickel metal hydride and lithium ion are good with in terms of specific power. So a lot of this has been covered already, but just to touch on energy storage on a larger scale, for example, for UPS, really to scale up you need cheap materials. But I think one point that should be made is, in addition to the materials, we should also consider the process, the cost in the manufacturing process, and scaling up a lot of these, the source of this. And in some technologies there might be maintenance issues, and cycle life, capacity, and shelf life are things to be considered as well. But really there's been some talk about advanced batteries, and right now it just seems that the big hurdle is the cost. And how do we address this problem? Well, there should be increased, there should be resources available for various institutions to do R&D and explore some of these low-cost alternatives. So I'll just go, here are some examples of energy storage actually demonstrated. The sodium sulfur has been used in Japan by the Tokyo Electric Power Company, and I believe they have I think the numbers are a 6 megawatt and 48 megawatt hour system. There's some other technologies, zinc bromine, Lithium ion has also been scaled up by Saft. And these are just some applications used in buses for propulsion systems. Santa Barbara and Nevada have been working on that, just to give some idea of uses of these different battery technologies. So what I thought I'd do here now is just kind of make a table and put out some numbers just to compare some scalable battery technologies. And of course, as you might notice, it's heavily biased towards lithium ion. That's just because lithium ion is more of what my background is. And what I do here is compare 3 different types of lithium ion batteries with lead acid and nickel metal hydride. And lead acid has been mentioned, of course, because it's the low cost. I also show theoretical specific capacities in milliamp hours per gram and the specific energies in watt hours per kilogram. And so really now let me talk about some of these individual lithium ion chemistries. Lithium cobalt oxide is an expensive material, and so there's a disadvantage there. Lithium iron phosphate is an exciting material now, and I think the subsequent speaker will cover this more in detail, but it's more environmentally friendly, and the cost is lower. And I have an asterisk here with this vanadium compound, because this is an interesting compound also, and the reason I have an asterisk is one way it can be made is using a synthesis using a carbothermal reduction process, and I'll get into that in more detail. But on a scaled up level, that might be a feasible way. Again, with saving the money in terms of cutting out steps in the process of making material might compensate for high costs of materials. So I just thought I'd do a back-of-the-envelope calculation and just say, for example, a use of 6 kilowatt hours per day, and how much capacity would you need? And just a simple idea is if you consider a house, powering a house, something where you have a battery that goes to 50% discharge, you would, for a day, need 1,000 amp hours. And then this, for 4 days, let's say this is used in conjunction with solar power. It's bad weather for 4 days or so, and this is what kind of capacity. And similarly for a UPS, for emergency backup systems, or just in use in a very sunny climate where you can rely on sunlight for every day. These are some numbers to compare. So these are just simplistic, naive calculations. But now let me just talk a little bit about batteries in general, and then I'll get into nanomaterials. I'll just touch on this briefly. Some selected battery technologies, the chemistry. Lead acid is at the anode. You have lead oxidized to Pb2+, and on the discharge. And at the cathode, you have lead oxide. These are the reactions, and both form this precipitation of lead sulfate. And so this is the overall reaction, but generally you'd want to avoid gassing. Lead acid is, I should mention, one of the oldest technologies, and I like the comment before that someone made about sometimes just using something that's simple and that's been tried and tested. Excuse me. Now, and then this is how sodium sulfur works. This is actually a picture of a sodium sulfur battery made at the Naval Research Laboratory, as it turns out. This was used for satellite applications. And but sodium sulfur is a high temperature battery, so with you need liquid sodium, and this is the reaction on discharge, and then the cathode, you have sulfur being reduced. So those are just a few basic chemistries. Now I'll just go into lithium-ion cells. And how a lithium-ion battery works is lithium ions are shuttled back and forth between the anode and the cathode. And usually this schematic here shows a discharge where the lithium ions come back out of the anode, which is a carbonaceous material, typically graphites of different morphologies. There was a list of different carbons presented earlier, and turbostratic carbons have been of interest in this too. That's just an aside. But how it works is the lithium ions go back and forth between these two materials, and so you need an electrolyte, lithium-containing electrolyte. And then so what kind of material makes for a good lithium-ion battery cathode material? I should also, I forgot to mention earlier that the cathode of the lithium-ion battery is usually what drives the cost. And the lithium, what you need is a material that intercalates reversibly. Lithium can go into the material and not change the structure all that much, and that gives it its reversibility. So some materials that have this property are lithium cobalt oxide, because it's a layered structure where you can have all lithium, all layers. You can also have materials that have interstitial sites, and then they accept or reject electrons. And once again, just with this schematic, then on discharge, lithium comes back out of the carbon and goes back into the lithium metal oxide that you started with. So just to correlate this with a general cycle profile, if we start with the battery just assembled, a lithium-ion battery, as we charge it up, we're increasing the voltage, and the plateau where the redox potential is, that's where the lithium transfer takes place. You extract the lithium out of the material, and about 4.2 volts corresponds to about this much lithium taken out in the case of lithium cobalt oxide, which is a good model compound to use to explain this. And then the reverse is true, of course, on discharge. And so it's all about just trying to get materials that have the highest specific capacity. So now that I've talked a little bit of background on lithium-ion batteries, let me just show how do we select materials and what's useful. Lithium is, of course, a very light element in lithium chemistry. There is a lot to study as far as lithium goes. There have been a lot of developments with lithium-containing compounds. And first you have the classical materials. There are some companies that actually manufacture one-third, 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 that is cobalt, nickel, manganese, variations of that. And then you have lithium manganese oxide has also been an interesting material because of its high energy density. You also have a family of vanadium compounds, and there are some low voltage. There's interest for low voltage applications. Now, then you have phosphates also, and you have a lithium iron phosphate, which is now being produced, and there's also this compound I mentioned earlier. And then as far as the anode materials, I think there's less focus on anode in general than cathode, but mostly it's carbons, different types of carbons. There's also been some work on nanomaterials as far as tin, an alloying reaction, and then lithium titanate is a very interesting material. So nanomaterials, this might sound surprising, but they can be either good or bad in lithium-ion batteries, and it depends on the different material or the different application. In the case, here are some examples of interesting nanomaterials. Lithium iron phosphate, which is produced by Fostech and NEI, and then that lithium vanadium phosphate compound earlier, which is produced and used by valence technology, where they leave some small residual carbon left behind, and lithium titanate. I think these are some areas of interest in nanomaterials. There's also work on polymers and nanoscale domains shown here, and then with nanotubes, of course. A lot of people touched on nanotubes, but there's interest in use Actually, I've been approached at conferences to take some of their electrode material with nanotubes and make batteries out of it. So there's a lot of interesting research in nanomaterials and lithium-ion batteries. I won't dwell too much on this because I think this will be covered later, but lithium titanate is a very interesting material because one of the things about nanomaterials is you have high surface area, and this allows for fast charging. And so there's a lot of interest in that. I showed a picture of a soldier early in the presentation, and one interest is having someone who can recharge very quickly. And it's a 1.5 volt cell, and I won't go into all the details of lithium titanate, but let me just highlight some of the advantages of, just repeat some advantages of nanostructured electrodes. The accommodation of strain between insertion and extraction. You don't want the less strain you have, the more reversible generally. There are some other advantages in terms of electron transport. And I'd like to just show this data because this is a discharge curve using lithium cobalt oxide as a cathode and lithium titanate as an anode. As you can see, it's a lower voltage cell. Typically, voltages are around 3 with lithium cobalt oxide, or 3.8 rather, with lithium cobalt oxide versus carbon. And C means a full discharge within an hour. So we talk about C rates. C over 5 is full discharge in 5 hours. So again, you can see the specific energy is the area under the curve, the voltage versus specific capacity, and it tends to be lower with higher rates. But some disadvantages are there can be undesirable side reactions. This is an example of a bad cycle profile. Then there are some examples of use of nanoparticles, and not necessarily in the cathode material, but TiO2 and silica, for example, have been used to very small particles to increase conductivity. And I mentioned the carbothermal reduction method a few times, and essentially what it is use of grinding carbon in with a precursor, and there's a reaction of oxidation of the carbon. This is a very old metallurgical process, and this reduces the precursor and gives you a final product. And so there's a lot of interest in that. But lithium manganese oxide is an example of a nanomaterial, the downside to nanomaterials, because one thing that happens with high surface area is you increase the tendency of unwanted reactions, and that happens a lot with electrolytes and lithium manganese oxide. So I think I've touched on a lot of lithium-ion batteries in general and use of nanomaterials in them, and hopefully in the context of the larger problem of energy storage and technology, nanomaterials are in lithium-ion batteries have the advantage of the high rate. I think lithium titanate is a very interesting material, and that can be used. There's a lot of interest in low voltage cells. The carbothermal reduction method is an area of interest, and that can be an advantage in scaling up. And I'd just like to reiterate that if we can eliminate some steps in the process, even with a high cost of material, that we might be better off in scaling up lithium-ion batteries that way. Thank you all for your attention.
Very good. Thank you. We have time for questions.
I have a question. I'm wondering if you know any data on how the lithium-ion battery life cycle changes if you do shallow cycling versus deep discharge and charge?
Generally, it depends on, I mean, most of the time, if shallow charging, and again, this depends on the material.
I'm talking about shallow discharging, I guess. If your battery, instead of going, you know, to 80% discharge, if you were going, let's say, 5% or 10% discharge.
Right.
How does that affect the lifetime cycle?
I think once you get below a certain depth of discharge, and in the case of, let's just take lithium cobalt oxide versus carbon, for example, you get to a point where when you get below that level, such as if you charge lower than 2 volts, if you go from 4.2 volts to lower than 2 volts and you cycle that, you really lower the capacity. You increase the capacity fade rate. I think in that example, let me just point to that example, but I think that you're pretty much okay. You have very minimal capacity fade rate to any voltage range smaller than that is going to a lower cutoff voltage higher than 2, higher than 3, I should say. Typical cutoff ranges, testing ranges are with a C over 5 rate and between 3 and 4.15 or so volts for that.
What in your mind is the most common failure mechanism for the lithium-ion battery?
Well, one thing, and it's kind of funny because I spent so much time talking about these nanomaterials and battery materials, but really the electrolyte and packaging. The electrolytes in lithium-ion batteries are typically organic solvents with an LiPF6. That's a lithium hexafluorophosphate, and you have unwanted side reactions such as HF that form, and so you get gassing, you have unwanted reactions. I won't go into too much detail, but just nitrogen and oxygen and things like that. So the sealing and the packaging, and that's why scaling is an issue.
Is lithium titanate the best known material for anodes now?
Well, if you don't really care about what voltage cell you have, I would say it's a metal oxide. I don't want to say it's better, but because carbon is very cheap, and but lithium titanate is just it's got very minimal strain for a metal oxide. Usually, you'd think of a lithium compound like a metal oxide compound as a cathode material, but since it has such a low voltage and it's a zero strain material, it can provide a lot of feasibility and probably give a lot of high cycle life.
Any other questions? If not, let's thank our speaker again. Thank you very much. We're right on time. Our next speaker is Dr. Amit Singhal. He's the Chief Scientist with NEI Corporation. He's speaking on nanostructured electrode materials for energy storage devices.
Hi, good afternoon, everyone. I would like to thank the organizers for giving me an opportunity to talk about our work in the area of nanomaterials for energy storage devices. I also like to thank Arnold for giving a lot of background on lithium-ion batteries, so actually he made my job pretty simple. What actually I want to achieve here today is a take-home message that the nanomaterials are interesting. There is a potential, particularly in advanced energy storage devices, to improve the performance. But however, as Arnold also pointed out, the synthesis of the material is the key. In the sense, if we are going to make large-size batteries using nanomaterials, we have to develop processes which are easily scalable and also cost-effective. So some of the focus, and then it is possible that, and the challenges and materials will be brand new, because when you're going from a cell phone battery to a large size battery, things of reaction which were okay in, for example, the materials which are used in cell phone batteries are not, and there are certain reactions which happens with the electrolyte and the electrodes, which are okay when you have a very small battery, but they become unsafe as the battery size increases. What I did is, I know that for the last 2 days, we've talked about how the energy storage and devices and the electrical power applications can interrelate it. I've taken this slide from a Susan Scholar presentation, which was given at DOE Energy Storage System Conference in Washington in 2002. What it does, if you can see, I've divided it's actually, it has energy storage is divided for a grid application in 3 parts. One is bulk energy storage, second is distributed generation, and third is power quality. As you can see, the total energy requirement for the bulk energy storage are rather large. So I don't think that advanced batteries or advanced energy storage devices would make it for that kind of applications. Thank you. However, if you look around the power quality application, where the total energy is in the range of 30 watt-hour to 17 kilowatt-hour for the power quality application, for example, for end user power quality and reliability. However, the rates at which the power has to be withdrawn from the batteries are rather high. So that's really provide an opportunity for nanomaterials in terms of the grid applications, where the requirement for total energy is not significantly high. However, the discharge rate capabilities are significantly high. So and as I will go further in my talk, I will show how nano really improves the discharge rate capability. And that's where I think, in addition to the HEV batteries, where again the application really requires high power. The total energy density for the battery is in the range of 300 watt-hour to maybe a kilowatt-hour, but again, the requirement for the power is a lot more higher. So when you go to a large-size battery, what are we really looking for? Number one factor is the safety. For example, the existing chemistry, and I will explain that in a detail. What we have today, existing lithium-ion chemistry, which is used in a cell phone, if you can use the same chemistry in a car and it's more like a bomb sitting in a car, because at the hot summer, the temperature in the electrolytes are going to go up, and the reaction between the electrode and electrolyte is going to happen, and the battery will blow up. So the existing chemistry, which are used for small-size batteries, actually cannot be used in a large-size batteries. The second is the cost-effective. I mean, you can handle a few dollars increase in the cost of material when you're, again, dealing with the small-size batteries. But when you're going for large-size battery, those numbers start adding up, and that becomes things pretty expensive. And, of course, you need high energy density, high power, and you need a long cycle life. And some of the applications, you also need large shelf life. You don't want battery to just die if it's not being used. That may be a case in some of the power quality applications. So where is the nano and energy storage crossroads? And actually, at this point, there are 3 types of devices which have been actually used. One is lithium-ion battery. Second is it's a completely new idea which has not been really surfacing in the market, but it still is an R&D stage. Instead of lithium, can we replace lithium with something else like magnesium or yttrium? Because the magnesium is 24 times cheaper than lithium. And so can we make magnesium batteries? Third is the hybrid batteries. It's the idea, can we combine the capacitor and the battery together to come up with the new devices? And in all these battery devices, actually the work is being done at this point in terms of the nano, in case of lithium-ion, both at electrodes level and as well as electrolyte level. Because, again, the electrolytes today which are used in battery are mostly liquid electrolytes. They are toxic, they are very toxic chemicals, so as we increase the size, there's a possibility they start leaking out from the batteries. So can you use polymer electrolytes? And that's where the nano is actually being incorporated to improve the conductivity issues. But for this talk, I will be mainly focused on electrode materials. And same thing in a polyvalent. Again, in the case of polyvalent, as you increase the charge, for example, magnesium or yttrium, the charge density is much higher. So then the diffusion is a real problem in the metal. So that's where the nano can maybe solve some of the diffusion problems. And same issues are applicable in hybrid batteries and supercapacitor, where yesterday some of the people have talked about carbon nanotube, or maybe high surface area carbon, where the the electrochemical performance of capacitor can be further improved. I don't want to go into detail. My previous speaker has already given actually a good background about the lithium-ion battery. The point I just want to make here is, if you see the structure of these materials, this is the anode. It could be a layered, and it could be a spinel. Spinel means it has a 3D structure. So lithium can go on all three directions. And in the case of carbon, which is a graphitic sheets, the lithium can go in a two-dimensional structures. So fundamentally, as you charge and discharge, lithium ions are going in and out of the material. That's why these type of devices are called rocking chair batteries, because lithium is really rocking in and out. And so basically, these processes, these batteries are diffusion limited. So that's where the nano really plays a significant role. And as I was explained, as lithium goes in and out, in any of these materials, there's a volume expansion, either contraction or expansion. That creates a lot of stress and strain in the material, and that also, again, that's where the nanomaterial may improve the performance of the lithium-ion battery or similar rocking chair batteries. So when we take the example of nanomaterial, what are we talking? I mean, actually, there are two possibilities one can choose in terms of material. One, you can have a single nanoparticles. Let me just first explain the cathode geometry. Typically, in an electrode, you have a current collector, and the particles are surrounded with carbon particles. Carbon particles are giving electronic conductivity. So there are two possible scenarios. One, when you can have an individual small size of nanoparticles. Another possibility is you can have a large particle which has nanodomains. In both cases, if you look up the mathematical expressions, I don't want to go too much detail, but if you have a rate of lithium diffusion and some function, at the end, the current is whether d is the particle size or the domain size. As the d is decreases, the current increases. And m is depending on the diffusion mode, whether if it's a volume diffusion, as this would be in this case, or if it's a grain boundary diffusion, as would be in this case. In either cases, you can increase the power density by either reducing the particle size or reducing the domain size in the particle. So when we go, so why do we need, what is the promise of nanomaterial? What we are looking for? One, of course, I just said, you can get, since your diffusion distances are reduced, there is a higher specific capacity at high rates. As lithium ions goes in and out, there is a smaller dimensional changes that gives a less strain in the material, which actually is one of the reasons why batteries fail. Because what happens is, as the lithium ions goes in and out, the materials exfoliate, and actually and at some point, there's a significant amount of fracture occurs because they had so much strain and they start breaking off. And that can actually degrade the performance of lithium-ion battery. But the third interesting phenomenon, which nanomaterials actually provide, until now, once you have these materials, the existing chemistry or existing material, the most capacity is coming out by an intercalation process. Can you get a biosurface phenomena, which we, in an electrochemical term, is called non-Faraday capacity? The reactions are only happening at the surface of the particles, where the lithium or intercalating ions are not getting into the crystal structure, the reactions are reversible. And then the fourth possibility is maybe possible to innovate or come up with new chemistries which are not otherwise possible to use in a lithium-ion battery or some of these advanced energy storage devices. Okay, I'll just come to the materials. The lithium iron phosphate, it's a cathode material which has been getting a lot of traction, particularly for HEV applications. And there's a few reasons why it is so interesting. One, it has a high stability and it is non-toxic. The existing cathode material is lithium cobalt oxide. Cobalt is more expensive than lithium, more expensive than iron. However, Another problem with lithium cobalt oxide is it is oxide and it reacts with the existing electrolytes, particularly at high temperature. And that's we call thermal runaway reactions. And that can actually blow up the battery. But this has a phosphate molecule that makes it very stable. So it can be used in large size batteries. However, and the third interesting thing about this material is it has absolutely flat voltage profile, which I will show in a couple of slides. So it is cost effective, it is highly stable, it is non-toxic. Why people are not using it right now? Because it has a fundamental problems. Number one problem is the diffusibility rate is orders of magnitude lower than lithium cobalt oxide. So that makes it a battery actually doesn't really work at reasonable discharge rates. Second, it also has poor electronic conductivity. Electronic conductivity of lithium iron phosphate is in the order of 10 to the power minus 8 Siemens per centimeter. So for a battery cell to work, you have to diffuse lithium as well as you have to transfer electrons. So if the material has a poor electronic conductivity, again, the battery won't work. So in literature, if you look at the literature in last couple of years, there's tremendous amount of work has been done to make this material highly conductive, and also by reducing the particle size can be improve the diffusivity. So the approaches to solve the problems of lithium iron phosphate is have a nano lithium iron phosphate with a carbon intermittently mixed with each particles. And this approach has been actually so the carbon provides external electronic conductivity, while reducing the particle size of iron phosphate improves the diffusivity problem. Before I go to show the slide, and there has been a lot of researchers who actually have done this. But the main thing is, in lithium iron phosphate, iron is an oxidation state of 2. So if you start with all your chemistry, all your processes with iron 2, which is a very expensive material, so we come back to the same problem, the material is not cheap. So to make this material a viable technology for a large size battery, people have to use iron, which is 3+, which are the cheapest material available. However, with LiFePO4, the iron is 2+. So at some stage, iron 3+ has to go to iron 2+. And on the second hand, you also have to have a carbon in the material so that it can be highly electronic conductive. Well, here this is a high resolution TEM micrograph. At the beginning, we also had the same thought process that we can produce the lithium iron phosphate and then do the coating of carbon on the surface of each particle so that we can make this novel composite. However, the process is pretty tedious and it makes things very expensive. But here, just to show the TEM micrograph, you can see the lattice fringes from lithium iron phosphate, and you can see the amorphous carbon which has been coated by a vapor phase process. And the thickness of this coating is around 10 nanometer. This process worked fine. I mean, we were able to make good, reasonable electrochemical. We were able to withdraw reasonable electrochemical capacity. However, we were end up adding almost 35% carbon in lithium iron phosphate. That means effectively we have reduced the capacity utilization of lithium iron phosphate composite. Because again, there is a lot of limitation of this material in terms of if you want to use for large size batteries. So the goal is can you reduce the carbon amount, and can you produce in one single step the whole material. And then we developed a new process, which is a single step process where the nano lithium iron phosphate and the carbon composite is produced in one single step. And the amount of carbon is maintained around 5-8%. And it depends. So here is a lot of what this slide shows is in the same process, by manipulating the different processing parameters, one can achieve a very bad electrochemical material where the capacity is only 90, and by the way, the theoretical capacity of lithium iron phosphate is around 170 in the amp hour program. And Further improving it, we had 120, but if you can see the first cycle, the charge capacity and the first discharge capacity, what we call in electrochemistry, irreversible capacity loss, was still higher. Then we further improved the process, and we could get almost like 150 amp hour per gram capacity with only 3% irreversible capacity loss, which is acceptable for the battery industry. So because I wanted to show here, as I said in the beginning, there's a two type of material one can make. One where you have individual nanoparticles, and another cases where you have a nanodomains. So the lithium iron phosphate is the case where you have individual nanoparticles. Again, you can see that this is a field emission scanning electron microscope, and each particulate is around 100 nanometer. On the average, of course, there's a change in the size distribution, and then there's the aggregate size. What it means is in a powder, there are two sizes. One is, of course, the individual particle, but these particles are a little bit touching each other, so they have an aggregate. So that's the way we do it by using a light scattering instrument. And you can see, the particle has a very narrow distribution, and max around 150 to 160 nanometer. And the surface area of this material is around 20 to 25 meters square per gram. Because that's what you expect. If you have an individual nanoparticle, your surface area is going to increase. And here is just showing the electrochemical data. Here again, I have plotted a different C rate. One C means if your battery is being charged in an hour. If it's a 10C, your battery is being discharged in 6 minutes. So what the goal here is, can you reduce the loss in capacity as you increase the discharge rate? At a lower rate, which is C25, at almost 25 hours of discharge, the capacity has a full utilization. But the interesting thing is, even at a 1 hour discharge, we had almost more than 85% discharge capacity of the starting material, which is actually, and then on the top of it, if you do the cyclability of this material, as you can see, the material doesn't lose any of its capacity. It's pretty flat. And the interesting thing, this process is scalable, and we are actually supplying in reasonable quantities for the battery manufacturer and the automobile manufacturers to test this material. The second example I've taken it's a case where it is not individual particles. It's the nanoparticles with the nanodomains. The surface area of these particles are rather small. It's less than 0.5 meters square per gram. Now we want to see, can we still improve the discharge capacity of these cathode materials? This material is actually is a favorite material for aerospace industry. Most of the lithium-ion batteries in aerospace industry utilize similar type of composition. Again, it has a higher energy density than the existing cathode material, lithium cobalt oxide, and it is safer than lithium cobalt oxide. Of course, it is not. Recently, it has been found that this material is not safe enough to use in a hybrid electric vehicles, and now actually the aluminum is being replaced with the manganese to improve the safety of this material. I just wanted to show, this is the XRD graph showing that it's a single-phase material. I don't want to go too much detail in that. But as you can see from a FESM micrograph, it's a highly aggregated material. The surface area of this material is less than actually 0.5 meters square per gram. But the crystallized size, the domains, what we call, is in the range of 50 to 60 nanometer. And then we compare this material with the existing material with the same composition, and which is a coarse material where the surface area is around 1 meter square per gram, but the crystallized size is almost 500 nanometer. So they're much larger than this material. This is, before I show the comparison, I just wanted to show it has the good cyclability, and the capacity of this material is around 160 amp hour per gram, which is almost close to a theoretical number at low current densities of 640 watt hour per kg. Here, this is the comparison between the nanocrystalline lithium cobalt oxide versus the commercial material, which is exactly the same composition. And as you can see, at C over 5, yes, at C over 5, the capacity or the discharge rate capability of both materials is almost similar. But as you go to almost like a 6-minute discharge, the coarse material or the commercial material starts losing most of its capacity, while nano still maintains its 30% capacity. So the nano domains are also important in terms of improving the material's discharge rate capability. And the second type of device which we believe where the nano can really fit in, it's a asymmetric hybrid device. I just want to give you a brief overview of what that device is. The device is a half lithium-ion battery and half supercapacitor. So the cathode is a high surface area carbon, and the anode is an intercalating lithium material such as lithium titanate. So again, as the device is charged, the lithium ions intercalate in the anode, and the PF6 ions just absorbs on the surface of the high surface area carbon, and electrons get transferred. So the goal was here again, because this device was really focused for very high for the high discharge rate, fast charge rate. So if you have a coarse material and your lithium diffusion is kind of rate limited, then this device won't work for applications where you're looking for fast charge rate. And particularly, this device was really designed for in a hybrid electric vehicles where you want to use a regenerative braking system. As you brake, the energy is created. Can you charge that energy? Can you use that energy to charge these batteries? Again, here there's a FISM micrograph of this material. The surface area of this material is around 5 to 7, which is not significantly high in terms of considering the nanomaterial, but this material is composed of 100 nanometer crystallites. This is something in between the nano domains and nanoparticle, where the surface area has moved up, but also has nano domains. And again, here just to show what is the discharge rate capability of this material. Again, 1C is, as I said, is a 1 hour discharge, 5C is a 12-minute discharge. As you can see, even at going from 1C to 5C, it does not lose its capacity. The material is pretty much stable. And here I've plotted the discharge capacity as a function of discharge rate, even at 100% at a C over 2, which is 2 hour discharge, to going a 12-minute discharge, it lost only 4% of its capacity. On the other hand, when we did the commercially available same composition, a coarse material, it loses at a 5C, it loses almost 30% of its capacity. And when you go to a 10C, which is 6-minute charge, it loses almost 70% of its capacity. This is just showing a prototype device using this material, an asymmetric device. And this is just to show the cyclability. It's been cycled for more than 10,000 cycles, and it does not show any degradation in the capacity. Well, as my previous speaker mentioned, the lithium titanate, the use of lithium titanate actually reduces the voltage of the battery. So most of the device I showed, the asymmetric hybrid device, is the voltage is around 2.15. So if you're looking for a device which has a high rate, high fast charge rate, and if you want to increase the energy density of the device, you have to jack up the voltage. So then we started working, I won't go too much in detail, but we started working on material like tungsten oxide, which we have shown if you use as a coarse material, they degrade within, the capacity is only 60 milliamp hour per gram. However, if you use this material and if you can make this material to work, the device voltage can be increased from 2.15 to 3 volt. I have 2 minutes. So again, just to show what we can do, how the synthesis of the material can achieve different particle size and the performance of the material. Just to show here again, by controlling the processing parameters, we're able to control the primary particle size going from 100 to 150 nanometer to 50 nanometer. And it just shows because what you really want in nanomaterial, but ultimately these materials have to be packed in a polymeric batteries. So you want nice spherical morphology so that you can have a very high packing density in terms of you can have a high volumetric energy density. I just wanted to show a graph just to show that this is again compared with the red is a coarse material and the blue is a nanomaterial. It clearly shows at a 1C rate, the nano has a higher capacity retention than the coarse material. I'll just skip that. I just wanted to show one more slide. The third type of device, which is actually the nano may be the key to make that device enable. And the beauty about this material, of these devices, since the magnesium, the polyvalents are cheaper than lithium, number one. Second, it has been found that the activity in the electrolyte of these materials are a lot lower. So the batteries made of polyvalent could be much more stable. So they can be actually used for a long life. But however, the polyvalent ions have a large charge density, so you need to reduce the particle size. And just to show, this is actually a published paper. We worked with the Glenn Amathucci, Rutgers. And just to show here that when you take a 500 nanometer vanadium oxide, the material loses its capacity and its reaction is absolutely irreversible. While you go to nano V2O5, 50 nanometer, this is the discharge profile and is absolutely reproducible or absolutely reversible. I'll probably skip that. And just to summarize, I want to say the nanomaterial has a tremendous potential in improving the properties of different energy storage devices. It's not only the feature size which is important, it's the microstructure and the composition of material is also very important. And ultimately, we have to develop scalable and cost-effective synthesis processes to make these materials. I'd just like to acknowledge different federal agencies, the members of NEIT, and different federal agencies for funding this work, and our collaborators at Rutgers University and University of Texas, Austin. Thank you very much.
We have time for one brief question.
I was just wondering if you need to add diluent carbon to the lithium iron phosphate compound with carbon in it, usually to get the utility of the material?
To add more carbon?
Right. Usually when you make electrodes, you add
you add this usual same 10% of the carbon.
Okay.
Thank you.
No, that's fine. I get the answer.
Okay. Very good. Let's thank our speaker again.